Hello all. Due to the new regulation from the NTNU, we are no longer allowed to give lectures, and since I basically have mainly 2 lectures left, I will try to cover them during the next 2 weeks. First and foremost, today I will cover something called scene graphs, which will be today's talk. What we will have left then in the curriculum is basically shadows and reflections, and a little bit about normal mappings. And these things I will talk about next week. Today we will talk about data representation and data management, basically. How to efficiently represent data and to make few rendering calls and so on and so forth. So this week I've chosen to just have a talk through of this week's lecture. You have these slides available on the wiki page, so I will load the newest version there after this lecture is finished. So you will find that down here as usual. Okay, so today we'll talk about scene graphs. It's basically a way of organizing your data so that you can do with fewer code lines and also fewer calls to OpenGL. Because up until now we've basically been dealing with either very simple primitives or like last Thursday we learned how to load objects. But up until now we dealt with relatively few objects at a time and relatively few primitives. In a more advanced scene you would be interested in having many more objects and much more geometry and different scenes to interact with. For example, in a game you would like to have different levels and so on and so forth. And then we need other tools to our disposal to be able to keep track of their relations and their movements in the world. So let's go back to this car example that I showed some weeks back when we talked about transformations. And particularly here you see parts that can be reused again, for example the wheels. So the mesh for a wheel can be used 4 times here. And the difference between them is basically translation, rotations and scaling. But that's easier said than done. Of course, moving this so they always align correctly with the car and attached where they're supposed to is easier said than done. So to do that, we need some additional structure that tells us how things are connected and how they will move together. And for this we need some sort of hierarchy. So as I already mentioned, doing this manually in code is very slow and you get a very long and bulky program that is not easy to deal with. So we have to find better ways, and the way is basically to build some relationship between objects, then code these relationships as matrix transformations, and then create a hierarchy of objects, and we update that hierarchy instead of updating each part individually. So we basically define a hierarchy, we load individual objects, we attach each object to this hierarchy, and then we operate on that one. Now behind this lies scene graphs. And there are 2 possibilities. If the scene is not too complicated, you can write your own. That's a good exercise, and you will learn quite a lot about how to deal with these structures. Alternatively, there are many tools out there like OpenSceneGraph that you could use at your disposal, and when things get much more advanced, it's always an idea to revert to these sort of existing technologies. So what kind of hierarchy are we talking about? Now, think a little bit about how movement of limbs on a human or a robot will relate to each other. So for example, head, arms, legs, they will always move with the body movement, right? They cannot move without it. They will always follow your body. However, your head, arm and legs can also have movement independently. That does not affect the body's world position at all. And the same goes for the arms. with respect to hands and hands with respect to fingers. So you can move your fingers without moving your hand, but you cannot move your hand without your fingers moving with them. And if you draw these relations, what shows up, as with so many other things in nature, is a tree structure. So that will naturally describe such relations. So here I just drawn this. Of course, this is an oversimplification of the movements of the body, but it captures the essence. So basically, as I said, the body is on top, and everything below it will move with it. So head, left arm, right arm, and fingers, for example, will move with the body. The head, though, of course, the eyes will move with the head, and the mouth will move with your head, but movement of your head does not necessarily need to move your body, for example, or will not result in movement of your body in most cases. So this is a natural structure in order to describe these movements and how they relate to each other in space. Now, a scene graph is basically, said straight out, a method for keeping track of many scene objects, including their transformations and properties, basically. And the primary focus is to represent 3D world as efficiently as possible and make do efficient rendering. Make as few code lines as possible, and also, more importantly, as few OpenGL calls as we can. And for this disposal, we basically use scene graphs. So this will be important also in assignment 2 if you're going to do some complicated things or include many objects. It will always be an idea to try to set this up as some sort of scene graph. Okay, so basically, as we saw on the previous slide, we have nodes, for example, body, head, eyes, and they're connected by edges or links, as we say. So nodes are linked in trees, or, as we will see later, in a more general sense, a directed graph without cycles, or so-called DAGs. I think that many of you will know these structures already from algorithmic methods, or algorithms and data structures, which is also called. So you will really get used for that course in the practical way here. And once you have described your scene as such a structure, all those very nice techniques that exist out there will be at your disposal to be able to make efficient graphic programs. So typically, many nodes has one parent and a vector of children. So for example, if we go to the previous one here, your left hand, it has 5 children, and it has one parent, the left arm. Your body has 3 children, but it doesn't have any parent, and therefore it's called a root node. The digits, or your fingers, doesn't have any children, neither does your eye or your mouth, and therefore they're called leaf nodes. Now we will deal with many types of nodes in a scene graph, but typically a node can describe objects in a scene, and then they're usually called a scene node. And if it is a scene node, it typically contains a pointer to some mesh, for example the wheel we saw, or it could be a mesh of an arm or the mesh of a finger. It has a local transformation inside it that operates on that mesh, as well as attributes. It also has access to a world transform that is inherited down from the parent. So if we go back to this tree again, for example, your left hand will inherit or get some transform from its parent, the left arm, and to figure out its movement, it will just multiply that matrix with its own. And basically, the left hand will then have a pointer to a mesh that describes the hand. And this mesh could also be used for the right hand, for example. So that's a bit of the point about this, that the same mesh can be used several times. So you only need to make it once and then just have pointers to it from these nodes. You can also have so-called transitional group or state nodes. And they can, for example, group several nodes together and switch between them depending on some state. It could also put together nodes that are rendered in the same way using the same shader, for example. So here you have a possibility to do coding more efficiently also. We will see more examples on transitional group and state nodes later when we start to talk about particularly open scene graphs. Now, typically the whole tree, for example, doesn't necessarily need to describe a body. It can also describe the world or the whole scene. Of course, then the tree becomes a bit more complicated, but that's usually the way you can do it. Or, of course, as we said in a more general sense, it can be described as a DAG. So what happens is that a world transformation, when it comes to movement, a world transformation is passed down from the parent, and then the node's local transformation relates to this one, relates the relevant mesh with respect to the parent node through its local transformation, rather than translating the mesh from local to world space as we've seen before. So as we talked about on the transformation lecture, you basically took your local mesh and then you moved it into the world space scene. What is very efficient with this tree structure is that only thing you need to do now is to relate it back to the parent's world transformation. So you only need to simply multiply your local transformation with the world transformation you receive from the parent, and then this will place you in the world space. And that's really the simplicity of having such a background structure. And another thing which is really important with the tree is that to determine the movement or the model matrix of any node, you basically traverse the tree and multiply the matrices along the way. And there are many methods for traversing a tree, as we know. Many of them are using recursion, and in that sense you could do a very, very efficient program with very few coding lines. Now if the tree doesn't change, you can with advantage store these resolving matrices, so you don't have to traverse the tree every time you want to do some sort of operation. And then you only traverse the tree if it's updated, if you add or subtract nodes from it. Very importantly also is that a good scene graph employs what is called culling of objects not seen on the screen. So basically, I won't talk so much about that today, but you can say that any object in some node has a bounding volume, and every single node that follows after that, its children in the same branch will also be bounded within that volume. And this fact you can use to tell if your object is colliding with another object, for example, or you can also use it to tell whether or not it's within the frustum of the camera, basically, whether or not you should render it or not, basically. It should also have some state sorting properties, such that similar objects are drawn together. This to avoid overdrawing. And the point is basically to reduce a myriad of OpenGL calls down to a few simple ones. And also, as we'll see when we start to talk about Open Scene Graph later, you have a lot of utility libraries that will help you to manage window handling, object loading, image textures, and images and textures, and so on and so forth. Okay, so here is a standard tree for a scene. Now, the way this tree is built is really linked against how Open Scene Graph, which we'll talk about later, links trees together. And you have your root node, which is the world, and then you have light. In this case, this will be light that is global, basically, which is light in your room or your world, for example, sunlight. And of course, naturally, this light doesn't have any children, and it's on top of the hierarchy because it doesn't really get affected by the objects in the scene. You can, of course, also have local light, you know, as we saw in one of these 3D Pac-Man games I showed you a week ago. where the light could, for example, be following some objects. But of course, again, that light would have no children. But here it's basically world light. And the or global light. The camera, of course, does not have any children either, and so it's high up in the hierarchy and doesn't have any more links underneath it. Then, of course, you have these group nodes that groups the different geometrical features of objects together. So, for example, if you do a transformation on group 1, then all the following meshes further down the hierarchy will move in that same way. If you do a specific transformation from group 2, then all of those meshes under group 2 here, which are colored blue, will also move in the same way, but now they will not affect the ones connected to group number 3. And as I mentioned here, the important thing is that each branch here basically represents some matrix operation. So the parent passes its matrix on, and it does this in a recursive way. It's shown a very simple pseudocode here. Right? So to figure out where a particular object or a limb or whatever mesh is in space, you basically follow the path from the world to the relevant node, and you multiply the transformations along the way. Then you will know where it is located. And I think basically I said most of the other things here. Group nodes I talked about. Leaf nodes, yes, as I said, the geometry, camera, light are basically leaf nodes in this case. And to repeat, they're basically nodes without children. Now, the geometry here does not necessarily need to be a leaf node, but it always is in open scene graph, which we'll talk about later. I will show some example now where the geometry can be higher up in the hierarchy, and also the tree I showed you that described limb movement on a human. The geometry is also further up the hierarchy, so it does not necessarily need to be a leaf node. Nodes can also contain other properties, like materials, a material's color, its texture, shaders, for example. These correspond to so-called open GL pipeline states. And an important thing is that properties of a node roll through into children. That's basically inherited. So if you don't set any property for a particular child, it will just keep the parent one. If you override it, then of course then you will have a new property which overrides the parent one. And this is really much linked to inheritance, which you know from object-oriented programming. So, to emphasize the importance of how you compute transformations through a scene graph, I'll take some particular examples on scene graphs and transformations. So just to repeat a little bit, a scene graph basically provides a parent-child relationship for matrix transformations. So it provides the structure to help decide what operation to apply for any given object. So typically each node represents a local space. Remember back to making triangles, for example, and particularly lab 3, where we had all those triangles moving together. You were basically making a triangle in local space and then hooking up to the others using these different matrix operation. But the point is here that each node represents a local space, and it does not need to care about the operations higher up in the hierarchy. It's basically just handed down to it, and then it just relates itself to its parent. And that makes it much more easy than if it should have to relate itself many generations above. As I already mentioned, each node receives the transformation from parent and multiplies with its own matrix. And it passes it further down the tree or DAG, depending on the structure you basically use. And importantly, or as we also saw earlier, all operations at one level of the tree will affect all its siblings further down on that branch, but it will not affect anything further up. And of course, operations done at the root will affect the whole scene or the whole structure or the whole object that tree defines. So I particularly liked this example taken from the universe, basically. How galaxies relate to the so-called local group. The local group is basically just a big collection of many neighboring galaxies, like our own Milky Way, where is our solar system is moving through, and also a neighboring galaxy called Andromeda, for those of you who know about these things. And then, of course, the Sun is one of the stars in the Milky Way. So is Betelgeuse, the upper left red star in Orion, if you've seen that on a dark night. And of course, you have Alpha Centauri is another star, and a myriad of other stars. Then, of course, we have our Sun, and around our Sun revolves the Earth, Venus, Mars, and Mercury, Jupiter, Saturn, Uranus, Neptune. We just draw 3 of them here to make this a bit more explicit. And of course, around the Earth and Mars, you have moons orbiting that also go for Jupiter and Saturn, and so on and so forth. Now, the point here is not to have a lecture in astronomy, but the point is, if you, for example, want to describe the movement of our moon around the center of the Milky Way galaxy, or even more complicated, with respect to the local group, that movement is pretty complicated. So instead of doing that, the moon relates to the Earth above it, which relates to the Sun, which relates to the galaxy, which relates to the local group. And then you basically have a chain of matrix multiplications that you do by traversing this tree. So again, here you have this natural thing that the solar system, all the planets below, like Earth, Venus, Mars, will move with the Sun, but the Milky Way galaxy will not move with the Sun, so everything above will be unaffected by the Sun's movement. With some exceptions on very minute gravitational effects, but we basically look away from them here. Right, so if you should simulate this, for example, any mathematical operation you perform on the galaxy will affect all the members following down the branches. Now, here's an example of how you can simplify a problem. So if you want to describe the moon's orbit around the Sun, it has a quite complicated movement. It's basically 2 ellipses. So you have an elliptical movement of the moon around the Earth, and then you have another elliptical movement of the Earth around the Sun, and you put them together, you get this nice curve here. But of course, if the moon just care about its movement with respect to the Earth with its own local matrix, it just needs to describe an ellipse. And then, of course, handed down from the Earth's movement around the Sun, you have another ellipse, and the product of these 2 transformations will result in this pattern, which is much more complicated. So you can see the way this way of structuring your scene will simplify the calculations you need to do. So I just show some example pseudocode here just to make it clear how you could define this. Notice that this is pseudocode, so the syntax here is not necessarily all that exact. It's just to make it clear and explicit. I will show right afterwards an example that is a bit more complicated, which basically you could read to get insight into this, on how you would program your own scene graph. But for now we just make it very simple. So a simple node here is just defined as a struct. In reality, you would like to make this an object or a class, for example. So you'd like to perform this world matrix for the moon, which is the product of all these other matrices, and to do that, you basically make a structure. Inside that structure, you have a number telling you the number of children that any given node have. Yes, as I told you before, you have a mesh pointer. In this case, that mesh pointer will be a pointer, for example, if you talk about the Sun, the Moon, and the Earth, that can be a pointer to a sphere mesh, for example, that you reuse several times, since all these can be described as spheres with just different colors, for example, or different properties. Then you have your local matrix, which basically, for example, which tells you how the moon moves around the Earth. And then you have a world matrix, which tells you everything that happens above in the hierarchy. And then you have a set of pointers, or an array of pointers, to the children of this particular node, which is, of course, of the same type as itself. And then you have the alternative to also draw things at each node, which we just put up here. You don't always do it, but you have the possibility to do it. So once you have that struct, you can basically easily compute the matrix by using this recursive function showed in pseudocode here. So basically you have a recursive function where you take in a pointer to a struct, which we now call current node, as well as its parent role transformation. And then all this function need to do to compute this rather complicated movement that will be the result of this hierarchy is basically to take the parent role matrix and the current node's local matrix and multiply them together. And then you run through all the children of this current node, and you basically run the same, you call the same function recursively. And the world matrix of those children will be the new matrix that you that resulted from the multiplication above. So it's very simple and to describe this in code. Of course, in the real world it's a bit more difficult, and I will just show an example of a cube robot, basically a robot consisting of cubes, and I recommend you to read this to get started if you want to program your own scene graphs. It's also a good exercise, even though you end up using OpenSceneGraph as a tool. So you can click this link and download, let me see, and download, let me see if I find it here, download this PDF file here, basically. So if I click on that, I basically get up this this tutorial. So basically what it is to make this robot out of different colored cubes in different sizes. And this robot also moves slightly if you run that program. Now, I won't talk about details on everything, but I'll just show you the node class as well as the recursive function that updates the transformation that makes this thing move. So typically you make a class called CNode, and in this class, of course, you have all your variables and vectors that you need. For example, pointer to parent. You have a pointer to a mesh, in this case, which are all cubes. So you basically reuse the same cube to construct this whole robot. You have, of course, have the world transformation that's inherited from your parent. You have your own local transformation. And you have the scaling of your model. And, of course, its color. And then a vector or pointers to all your children. And then you have functions up here that operates on these variables. So for example, you have a constructor that basically initializes all the variables, and you have a destructor that removes this one once you're done with it, basically. And then you have functions for setting transformations, reading the transformations, getting the colors you would like to put on the relevant cube. You have a function that gives you the mesh you're interested in, and so on and so forth. And then, of course, you have these two virtual functions, and they need to be virtual, basically, for this to work. So basically, you have this update function, which is basically the one that does the matrix multiplication for you, and you have this drawing function, which is basically calling a OpenGL renderer. So you have that possibility to draw this parts of this robot at any node, basically. But I will just look at the update. I encourage you to look at all these functions, how you use them to read in different data, and so on and so forth, and how to draw and those sort of things. It's all described here. But I'm concentrating now just on the matrix multiplication. So basically, once you have this node, this CNode's update function is really simple. So basically, all you need to do is a if-else condition. So if this particular node now has a parent, it means that the world transformation that you're going to pass on down the hierarchy is your parent's world transformation times your own local transformation. If you don't have a parent, it means that you're a root node, and basically then the world transformation, it's basically your local transformation. and then basically loop through the vector of children, and that pointer to child number E, you just, for the pointer that points to all children, all E children, is basically calling this function again and again recursively. And the result should be this this robot, which is basically rendered using just one cube mesh, basically. So this is a nice way to get started. Okay, so let's go back to the talk. Now, we only talked about trees until now, but they're not always adequate, at least if you have more complicated scenes. So to be able to enable more functionality, you may consider a directed acyclic graph, which is basically a directed graph without cycles. And it's so close to a tree that you sometimes say that it's actually part graph and part tree. It's something in between a full-fledged graph and a tree. And now nodes can be used again in multiple branches. So for example, this could be very useful if two objects start to interact. And let's say these two objects were in two different branches, but now these objects start to bump into each other, or they shake hands, or do something like that, then they will affect each other's movements, and then you would need these branches to converge. And if two branches converge, you do no longer have a tree. But a DAG still has leaf nodes, which are basically defined as nodes that has no edges coming out of it, so it only has links coming in. You also have to prevent loops in the graph for it to be a DAG, and that you basically have if you put up the DAG in the way that is shown in this image here, which you can always do with a DAG, then you will have no links pointing upwards, and this will always be the case. So you have no feedback link from something further down the hierarchy up again. Of course, you get a more functionality on it, but they're more complex to maintain because it's a bit more complicated to traverse them. But since they don't have any loops, you can always do this recursively, and you could, for example, use depth-first search, which some of you may remember from algorithmic methods. If you don't, I suggest you go back and repeat some of that things, because it will become very useful for you if you want to use this powerful tool in assignment 2. Okay. So I think a good example is a tree down to the left here. Now, why is this a graph, not a tree? Well, it's because of node E here. Two branches are basically converging here through this node, and therefore it's no longer a tree. It's more obvious that this is a graph and not a tree. So here you could have, for example, three objects that interact in some way, for example, movement-wise. And of course, you have the possibility, if you have one mesh that you use and use again, you could have these different paths coming down, and if it goes through these three first ones, you basically inherit a color from the parent. If it goes through the fourth one, you could change this color, for example. Probably not the best example, but anyway, it shows that you have some more flexibility by choosing DAGs. Also, the fact that objects can interact is probably a more interesting feature of it. And of course, if the scene becomes really complicated, then of course the DAG will also become quite complicated. And I'll get back to that, because if you want to build your own scene graph, which we encourage you to do because it's a very good exercise in learning algorithms and also understand how you traverse trees and also basically put all these things together, you need to write a model loader, you need to write a tree hierarchy, you need to deal with node deletion and addition because you would like to add and remove nodes, you have to write a traversal algorithm, you probably have a lot of examples of that from earlier books in algorithmic methods, and you need to write an optimizer to clean up the tree whenever that is necessary, to not overuse memory and those sort of things. And to get started with this, I recommend again this tutorial I just showed you with this cube robot. But if we go back to this very difficult graph here, then it becomes very difficult to make your own scene graph, basically. So For this, we have tools at our disposal, existing scene graph libraries, which we may use at the disposal. And I will continue to talk about that in the next video. So I will end this video here, and then I'll get back to you with the rest of this talk in another video.